Hey there, so I'm Annika, and this is Chapter 6 of Physics, which is Momentum and Collisions. This chapter is going to have three main topics. We're going to look at momentum and impulse, the conservation of momentum, and elastic and inelastic collisions. Let's take a look. We'll start with momentum. Linear momentum, which is expressed using the variable p, is defined as the mass of an object times its velocity. We write this equation as p equals mv. Momentum is a vector quantity, which means it has magnitude and direction, and its direction depends on the direction of the velocity. So since momentum is mass times velocity, the dimensions are mass times length over time, this is v, and then the units are kilograms meters per second. In order to change the momentum of an object, you need both force and time. So let's look at the force equation. Force equals mass times acceleration. We can rewrite a, or acceleration, as distance over time squared. Then since distance over time becomes velocity, we can write that as mv over t, and we know that mv is momentum, or p. So we can rewrite this as force equals the change in momentum over time. And then we've simplified it a little bit by multiplying the t over to get the change in momentum equals force times time. So let's look at why that's important. So first of all, the change in momentum is called impulse, which we express with the variable j, not to be confused with the variable j that we use for joules. The relationship between impulse and momentum is known as the impulse-momentum theorem, and that basically refers to this equation up here, where impulse equals force times time. So we're going to look at some applications of that. So here are some conclusions that can be derived from the impulse-momentum theorem. The first is that objects with more momentum take longer to stop. Let's see, so if we have change in momentum equals force times time, we know that if we increase the change in momentum and we want to keep the force the same, then we also must increase time. So that makes sense. And a practical example of this is that a truck would take longer to stop than a car, which has a smaller mass. A second application is that the force is reduced by increasing the time interval of impact. So once again, if we write out this equation, this time we're keeping the delta p constant, and we're reducing the force. We would have to increase the time to keep the product of these variables the same. Let's do some practice. Number 1. The speed of a particle is doubled. A. By what factor does its momentum change? So first we'll start with the initial momentum, we'll call that p initial, of this particle, so we can call that mass times velocity. Now we want to double the velocity, so we're saying this v is becoming a 2v. The final momentum would be mass times 2v, or 2mv, which is 2 times the initial momentum, so it's doubled. That's the factor by which the momentum changes. Part B, what happens to its kinetic energy? So now we'll write out the kinetic energy equation. Kinetic energy equals 1/2 mv squared. This would be the initial kinetic energy. If we want to find the final kinetic energy, we would plug in the 2v again, so we'll get 1/2 m times 2v squared. And then this 2, when it's squared, would become a 4. So we would end up with 4 times 1/2 mv squared, or 4 times the initial kinetic energy. So that's increased by a factor of 4. Number 2. A 5 kilogram box slides across a table at 12 meters per second. A. What is the momentum of the box? So we have our equation for momentum, p equals mv. We're solving for p, and we know m and v, so this makes it pretty easy. M is 5 kilograms, v is 12 meters per second. We end up with 60 kilogram meters per second. That's the momentum. Part B. How fast would a 0.4 kilogram box have to move to have the same momentum? Now, we know the mass and the momentum, and we're solving for velocity, how fast it's moving. So we'll plug in the momentum we got from before, which is 60. We know the mass of this new box is 4 kilograms. We're solving for velocity. So if we divide both sides by 0.4, we get that the velocity, v, would have to equal 150 meters per second. Number 3. A 50 kilogram block moving to the east slows uniformly from 10 meters per second to 2 meters per second. How long does it take for the block to decelerate if the force retarding its motion is 7 newtons? So this looks a lot like an application of the impulse momentum theorem. Let's write out the equation. Delta P, or impulse, we can also call this J, is equal to force times time. Now we have to solve for impulse, or the change in momentum. So first let's look at the initial momentum. It was moving at 10 meters per second, and the block is 50 kilograms. So that's 500. And then the final momentum, it's now moving at 2 meters per second, so that's 2 times 50, which is 100. So we see that the change in momentum, or impulse, is equal to the final momentum minus initial momentum. Then if we plug in our numbers, we get 100 minus 500, or negative 400. So once we know this change in momentum, we can plug it into our equation. So now we get negative 400, which, by the way, the negative sign expresses the direction of the change in momentum. That's equal to, and we know that the force is 7 newtons, but it's going in the opposite direction of the way the block is moving, so we'll also call that negative. Negative 7 times time. Now if we divide both sides by negative 7, we can solve to get that the time for this change to take place is 57.1 seconds. Number 4. A 0.5 kilogram football is thrown with a velocity of 15 meters per second to the right. A stationary receiver catches the ball and brings it to a stop in 0.02 seconds. What is the force exerted on the ball? So once again, this involves force and time, so we're going to be using this delta P equals force times time. We're trying to solve for the force on the ball. We know that the time is 0.02. We know that the delta P will be P final minus P initial. And then we can solve for these two variables. So the final momentum we know is going to be 0 because the ball comes to a stop, so there's no velocity. The initial momentum will be mass times velocity, so 0.5 times 15. So we get that F times 0.02 equals negative 7.5. Divide both sides by 0.02, and we get that F equals negative 375 newtons. And again, the negative sign just expresses the direction of the force. So this means that the force of the football player is going to the west, or in the opposite direction of the way the football was originally traveling.